Hey friends, welcome back. The first question of the day, we have a bit of a conceptual one. We've got this function f of x, and we only know one thing about f of x, that the limit of f of x as x approaches 5 exists. It is a number, we don't know what the number is. Okay. And we're trying to decide if any of these three limits must equal that limit here that we know exists. Okay. So just thinking about it real quick, here, as x approaches 1, we could maybe say that here in the parentheses, 5 times 1 is 5. So as x approaches 1, the number in the parentheses is approaching 5, which is the same thing as this. And we would be correct in that sort of analysis. But before we commit to it, I want to get a little bit more formal on you, okay? And look at it like this. So if we have two functions we're dealing with, and let's say we have this function g of x, and I want to take the limit as x approaches c. And I happen to know that this limit exists, and I'm going to call it lowercase l. And it turns out I also have a function, f, and this time I'm going to use the variable y, not to confuse it with x. And I'm going to let y approach this number, lowercase l. This limit exists, and it is capital L, okay? So I've got a limit that exists and another limit that exists. And I'm going to leave some space because we're going to need to impose an additional constraint, but I want to ultimately conclude that if I take the limit, okay, of f of g of x, this composite function, I'm going to let x approach c. If I do this, then it will amount to taking the limit of the inside function, which will give me lowercase l, and then taking the limit as though this is a variable, and that variable is approaching the limit lowercase l, which I already know is capital L. Meaning I can sort of sequentially take these limits, as in I take the limit of the inside, and then whatever I get, I take the limit of the outside, as opposed to having to look at that function as an entity and then dealing with the limit like that. Turns out this is actually a pretty powerful thing, okay? But, as I promised, I left some space here because in order to actually conclude if this, then that, I need one more thing to be true. And either, okay, 1, f is continuous at, and I'll go ahead and call this like y equals L. So if the function f is continuous at the limit of the inside function, then we're good. This is totally going to work. Okay. Alternatively, this or, okay, g is not constant near x equals c. Now, this is not the formal way of stating the condition, but I want to keep it that way just conceptually, right? Meaning that whatever the function g is, g can't be completely flat and have a constant y value around c. If you're curious, the actual formal statement of this is there must exist a neighborhood that includes the value c such that g of x is not equal to L everywhere in that neighborhood except possibly at x equals c. That's like the formal way of saying it. But for now, just this is the thing. And it's a very technical thing because if this happens to not be true and that happens to not be true, you can come up with very, very like peculiar functions that break this idea. Okay, but either way, if these two limits exist, and if either one of these is true, then we're able to say do the limit of the inside first, then do the limit of the outside function. Okay, let's go and apply that to the previous example. So in this context, first of all, I'm looking at this and saying, okay, what is g of x? G of x is the inside part right here. So this is a case where I'm going to go ahead and write like, g of x is equal to 5x. Okay. if I take the limit of this, so the limit of g of x as x approaches 1, well, I can just say g of x is a continuous function, so if I plug in 1 directly, g of 1 is the same thing as the limit, so that would just be the number 5. Okay, so the interior limit exists. Now, do I know that f is continuous? I don't, because that was not part of the given. But I know that g is not constant near x equals 1, because g is this 5x function, which is a linear graph. So I guess I'm trying to draw it correctly from your perspective, like that. It's positive slope, and it is not constant. Okay, so we have this condition met. So as long as we can show that this limit exists, then we're good. Well, what is the value of L in this context? The lowercase l. The value of lowercase l is the limit that happens when you do this. So this, ideally, is going to equal the limit as y approaches L of f of whatever the output of g of x is. So we can say this is the limit as y approaches 5 of f of y. And this is the same as that because it doesn't matter what letter I use, as long as I have matching here and matching there, these are identical statements. So I know this exists, and it must equal that. Okay. Let's think about this next one. Okay, so in this context, the inside function, x squared plus 1. So I'm going to call g of x is equal to x squared plus 1. Well, can I take the limit of g of x as x approaches negative 2? Well, this is a continuous function, so taking the limit will give me the same result as if I just plug in negative 2 and say g of negative 2. Well, that's 5. Oh, now we're in the exact same scenario as before. Well, we don't know f is continuous, but we do know g is not constant near x equals negative 2. Why do I know it's not constant? Because this is a parabola, and we have this sort of nice parabolic thing, and around negative 2, I'm not constant. Okay, so this should allow me to say, well, this is the same thing, the limit as y approaches, and what is y approaching? Oh, this number 5. Y approaching 5 of f of y. And that is, once again, the same thing as what we have. Cool. On to the final one. So we go here and we say, okay, well, what is g of x? G of x is this interior function. G of x equals 5x over absolute value x. Now, I would like to take the limit as x approaches 0 of g of x to see what occurs. It turns out this limit does not exist. And the easy way we can do this without having to go through a lot of analysis is just to graph it. So I have 5x over absolute value x, hit the graph button, and we see as x approaches 0, from the left, we get negative 5. From the right, we get positive 5. The mismatch means the limit of g of x as x approaches 0 from both sides does not exist. So I guess I shouldn't even put an equal sign here. I'm just going to say it does not exist. Okay, so looking at this, we would say, well, we failed this condition. So we no longer have the guarantee that we can do this. It is possible that by pure accident, or perhaps by design, this might happen to equal this. It is possible, right? However, we cannot say that this must equal that. So we'd say does not necessarily equal the limit as x approaches 5 of f of x. So we would say false to the question, must it equal that thing. Now, let's try a variation that's a little bit more algebra-based. So, I look at this and I identify an inside function and an outside function. So I can write this as g of x is the inside function, and the outside function is sine of y. All right? So in order to do my cool new trick where I take the limit of the inside and then I take the limit of the outside afterward, okay, I need to check that this limit exists first. So I'm going to go over here and say, okay, what is lowercase c? That's what x is approaching. So if I take, I'll do this in pencil, the limit as x approaches 2 of g of x. So I have a fraction. I can naively say I would like to split this into the limit of the numerator divided by the limit of the denominator. However, we know better than that because the limit of the numerator itself is a continuous function. We can just plug 2 in, we get 0. And on the denominator alone is a continuous function, so we can just plug in 2. We also get 0. And when you get 0 on the top and 0 on the bottom, this behavior shows up as a hole in the graph. It is a removable discontinuity, and so we want to do something clever, aka factor. So if I factor the top and the bottom, well, I guess the top is already factored. I say difference of squares, that's going to be x plus 2, x minus 2. Then I'm able to say, since x is close to 2, but not exactly 2, right? That's how limits work. I'm able to say these two are not exactly 0, safe to simplify. Then what's left over is a continuous function on top, it's just a constant, and a continuous function on the bottom, x plus 2, so I can just plug in 2, and I get pi over 4, okay? Then, if I say, all right, so pi over 4 is what's going to happen to the limit of the inside. Now, if I let the variable here, which is representing the entire output of this, okay, if I let that approach pi over 4, I want to see if that limit exists. So I'm going to say the limit of f of y as y approaches pi over 4, the output of that limit. Now, incidentally, we haven't together shown or really discussed the continuity of sine, but I'm just going to go ahead and assert here, trust me for a moment, that sine is continuous everywhere. Which means I can just take pi over 4 and plug it into sine. And sine of pi over 4 is simply root 2 over 2. Okay, so this is the capital L. So the argument now is, we've established that these two limits both exist, and I asserted, trust me bro, that f, the sine function, is continuous everywhere, so it is definitely continuous at the lowercase l value pi over 4. So I'm able to do this cool new trick where I say, hey, I'm going to do the limit inside and then replace that with a variable and make that variable approach what the limit is. I'm doing the inside first, then the outside. So this, I can say, is the same thing as taking the limit as y approaches pi over 4 of sine of replacing the interior function with this variable y, and then I already know that that is root 2 over 2. And I'm able to do that. Now, let's do an interesting problem with this graph. Okay. So first thing to notice, here we have a discontinuity at 2. Okay. The limit as we approach from the left and the limit as we approach from the right mismatch. So the limit as x approaches 2 for f of x does not exist. Cool? Okay. So looking at this, we're thinking to ourselves, maybe kind of like the previous examples, where the inside function is g of x. So if we let g of x equal x squared plus 2, and we try to take the limit of g of x as x is approaching 0, x squared plus 2 is a continuous function, so we can just plug 0 in for x, and we get 2. All right? So, jumping back here, our first consideration has been met. We got it. Now, if I try to turn around and take the limit of f as the inside variable approaches 2, now don't be confused by the fact that this is y and this is x. It doesn't really matter, right? Like I could call this y and z for all that matters. This is just the input variable, okay? So as the input variable approaches the number 2, which comes from the inside of this, okay, I already know that this limit does not exist. So this condition is not met, which means we're not able to just jump down and say this is the result. So does that mean we give up, say there's no limit, and walk away? Well, it turns out we don't get to do that because of something very interesting. So if I go and I graph this interior function x squared plus 2, x squared plus 2, and I graph this, and in fact what I want to do is I want to stay close to x is 0, so I'm just going to go ahead and go from -2 to +2 on the x's and just graph this. Boop. We notice that as x approaches 0 in this graph, both from the left and from the right, due to the nature of this parabola, my output values are always greater than or equal to. That this right here is always greater than or equal to. Which means when I then take the limit as this thing, which we're basically calling y, right? So what's going on here? We're saying we want y to replace this. As y approaches the value of the limit that we get from the inside, right? So as y approaches the number 2, we're not actually approaching 2 from both directions. We're only approaching it from the right. Since this thing right here, which we're calling y, is always bigger than or equal to, as x approaches 0 on that graph I have shown on the calculator, this y is approaching 2 from the right. So on this graph, once again, not getting confused by the fact that here the input variable is labeled x, right? This is our y, and the output of this is the y value in this graph. As I approach from the right, I get 5. This limit actually does exist. So just because I fail some of these conditions doesn't guarantee that my overall limit doesn't exist. It just means I couldn't do that cool trick. I guess this is a separate cool trick, but analysis, very important. So, similar note, what if I look at this? Okay, so this time, the g of x, I guess I'll call it h of x this time instead of g. H of x is equal to 2 minus x squared, right? Okay, so I'm going to take the limit as x approaches 0 of h of x. This is continuous, so I can just plug the 0 in. This is 2 minus 0 is 2. Okay, so I'm in a similar situation. However, if I turn around and I graph this as 2 minus x squared instead of x squared plus 2, and then I can delete all of this. We already know what the graph looks like. It's an upside down parabola. So as x approaches 0 in this graph, from both sides, notice the output values are always less than or equal to. And if I call this the y, and I'm setting up my limit like before, then the y values here are not approaching 2 from both sides. They're only approaching 2 from numbers that are less than 2. So then if I turn around to my graph and say, this y is now the input variable for this graph, my input variable is approaching 2 from the left, so I'm approaching a value of 0. Once again, I can evaluate this limit. Now finally, if I go over here and say, okay, this time, this right here, we'll name this something brand new. We'll call this like j of x. J of x is equal to 2x squared. I can take the limit as x approaches 1 of j of x. This is continuous. Plug in the 1, I get 2. A lot of 2's. It's on purpose, I promise. Okay, so now let's take a look at what 2x squared looks like. That's just a regular parabola. Boop, delete the x. That should work. 2x squared. Okay, but this time, x is not approaching 0. X is approaching 1. So as we approach 1 from both sides, notice that we're not always greater than or equal or always less than or equal. We're approaching the y value of 2 from below and from above. Ooh. So now this gives us a problem, because we would try to say, is this equal question mark to the limit as y approaches the number 2, right? Because that's the limit of this output of f of y. And the problem is, we already know there's a mismatch between the left and the right-sided limit. So this does not exist. Very important distinctions to make here. And so if I want you to take away one thing from this example, it is that when you're taking limits and doing calculus in general, always carefully analyze what you're actually working with, meaning look at the symbols, think about the graph, think about the function, try to turn it into a behavior you can understand. Because oftentimes that's how we get answers that don't immediately jump out from just looking at the setup of the problem. So hopefully that progression made sense. And in intro calculus, most of the problems that you have to solve, you get to just use your intuition. In the sense that if I have a composite function and I just want to say like f of g of 5, for example, then I would say g of 5 first, get an output, then plug that output into f, and then that's my answer, right? So in this case, what we're doing is under, suitable conditions, we're able to take the limit of the inside, get a number, then take the limit of the outside using that number we just got, that little l, and that's our answer. Right? This is really cool because, one, it works in most of the examples we have to deal with. And number two, it breaks in very specific cases that allow us to discuss what to do when it breaks. And those become very interesting conceptual problems and also become great test questions, right? So as you're studying these things, I want you to try to pay attention to why we care so much about establishing certain things to be true. Because when something breaks, you might not be able to make the conclusion you thought you could. And when you're being tested, a lot of the questions tend to address these nuances and specifically target those cases where you can't do what just feels intuitively obvious, right? So, as always, thanks for tuning in and study hard. I will see you guys next time. Peace.